Hello, everybody. Just so you know that you're not getting taught by someone she picked up off the street, I have solved a question on the world's hardest mathematics exam 2 years in a row. I developed a new branch of mathematics as a sophomore in my pure mathematics major, and I solved an unsolved problem. I have about 100 average on every single math course I've taken here, and I have taught in every single math course I have taken here. So this is my hobby. This is what I do for fun, and I'm really, really excited. I get to teach you all. A few things. A lot of you here are in Calc 3, but that does not mean you know how to learn math yet. So you've learned how to survive Pearson and doing the examples and clicking and clicking and clicking, copying Chegg, and then passing exams with C's. Okay, so that's not learning math. So in Calc 3, there's really only one way to survive this, and it's to do the work. So if you're curious about how to get a good grade, do the readings for the section. I'm going to upload those tonight to D12. I'm scanning them all because I have a hard copy of the book, so you'll have an opportunity to see everything there. Do the problems, because otherwise it's not going to go well. So if you have problems keeping up, I always respond to emails basically within the same day, if not a few hours. I use my meal times to catch up on email. So pretty much, if you get me before a meal, you'll get an email response back. Okay. Math is hard, so it's going to take time, and it's going to take a lot of your time. So raise your hand if you feel called to whatever major you are currently in, and sophomores, juniors, seniors. That's fantastic. So now you don't have an excuse because you're doing this for God, right? And I know they're going to over spiritualize a lot of stuff with things at ORU, but I will tell you this. When I realized that me showing up to my classes and doing reading when I didn't want to, and doing the problem set that I didn't want to, and showing up and doing and turning in work that I didn't want to, working hours I didn't want to, was worship. Because worship is going to be you obeying what God has asked you to do. So if God has asked you to steward your grades, to steward your expertise and steward your knowledge, do it for God if you're not going to do it for yourself. Okay? So I am a pen and paper math teacher. That means my full expectation for you is to have pens or pencil, I don't care, and paper. Okay? Nothing I will teach you is not going to be on this whiteboard so you can see everything happen. I believe in solving math problems as you learn math problems, and I believe in mimicking what you see and then practicing it on your own. If you still have questions, you can always email me. I'll make sure that's available and easily accessible on D12 as well. But is that clear? Because I want to set an expectation early. A lot of people, by the time they get to week 3, will have decided to basically stop trying. And then it's really, really fun negotiating how to get somebody from like a 50% to pass the class. Okay? So don't be that class. Show up, do the reading, do the problems, stop using Instagram 16 hours a week. Okay? Okay, vectors. I know all of you guys know who Vector is. He's the villain in but I'm going to draw you an arrow. And first I'll draw a point, just like this. Okay? This is going to be P. This is going to be Q. Pretty straightforward. This is a vector. This has exactly 2 components that we are interested in. This has a direction, and this has a magnitude. Oh, by the way, I like to be interrupted legitimately. So if you have a question and I'm talking, just shut me up and ask a question, okay? We call this point from where it comes the tail. Kind of cute. And this is the head of your vector. Anatomy and mathematics is a big part of learning mathematics. You'll struggle with problems in Pearson because you'll see words that you never actually studied from, guess where? The textbook. So read the book, it'll give you the anatomy, you'll understand what's going on here. So these are the 2 principles. You have direction and magnitude. That's the difference between vectors now versus just scalars. All the calculus you've done is with real numbers, right? So like 17. All you see is numbers. And so the concept of a vector is going to basically take just the magnitude side, and now we're going to put that magnitude in a certain direction. Okay? Any questions so far? As a matter of notation, math is a language, so we use symbols to communicate what we're talking about, to have a shared understanding of the language. So this is how we would denote such a vector with points. The tail goes to the head, so T goes to Q, and that is a vector. Okay, so what happens if you have a vector that has exactly 0 magnitude? So the magnitude is 0. What do you think that looks like? Yeah, it's a dot. There you go. So this right here is the 0 vector. And we have a special notation for this. We write the number 0, and then we put an arrow over it. In your textbook, when you can specify like different font kinds, this will be bold font in the textbook. However, I know all of your guys' handwriting is not good enough to distinguish between, regular typeset and bold. So always arrow off your vectors. That is one thing I will be picky about. Mathematics is precise. So there is now going to be a difference between what is going to be considered a vector versus what is going to be considered a scalar. So for example, if I told you x, that's just a scalar. That's just a number. The difference between that and x, what does this have that this does not?
An arrow.
Direction. So if I see in your work, you were using this when you meant this, I'm sorry. It's just not right. Okay, so be hard on yourselves with notation, because the more clean your notation is, the easier actually it's going to be to read, to memorize new concepts, and to go forward. So we can do different things to vectors. We can scale them. So if I decide to press the grow button and scale up a vector really large, I can take a vector v and I can multiply it by some scalar c. And so as c gets larger, we can make it grow. And if c is smaller, we can have a shorter vector. The idea is we're still in the same direction, but we simply chosen a different size. Make sense? So common sense says if c is 100, is that going to be a pretty long or a pretty short vector?
Pretty long.
Okay. In the eyes of God, who is so infinite and wise, is 100 a very big number?
No.
No. Okay, that was a trick question. Say this was 1 in comparison to maybe 10. Which one's going to be longer? Okay, so a lot of the first homework is just going to be, can you use common sense? And the pure mathematician is what I love here, because none of us have common sense. Now, parallel vectors. Everyone knows what parallel lines are, right? So it's when you have train tracks. These lines will never intersect. Now, I don't care about non-Euclidean situations right now, but in Euclidean space, these will never intersect. Okay, so when we talk about parallel vectors, it's going to basically be the same thing. They'll have the same direction. Now, it'll mean something slightly different, because these two directions are the same, even though the scalar multiple is different. But we don't care because they're parallel. So if you can take some sort of a vector, let's just use A. And if you can scale A, say by some scalar x, or if you scaled it by a different scalar, y, we would call these two vectors parallel. Because the only difference is the multiple that's telling them how big they can be. So if we can have positive scaling, then we can have negative scaling. So intuitively, what's that going to visually be? How's the direction going to change if instead of just scaling up by positive amounts, we now turn it to minus sign?
The head's on the other end.
Yes, it just goes the other way. So if this right here is some vector u, then going the opposite direction is going to be minus 1 u. So negation is going to then flip the order, or not the order per se, but flip the direction. Visual learners, raise their hand real quick. Oh, fantastic. Okay, sign turn. So this is kind of how this vector step works. It's pretty straightforward. The rules are pretty straightforward. And then now when we do analytical representations of vectors, we use components. So the most common thing you're going to be doing with vectors is components. So we specify how many parameters we want. And here's the thing, there's two sections in the text. They have vectors in the plane, and then they have vectors in three-dimensional space. And I thought to myself, well, that is a surefire way to make people more confused than they need to be, okay? There is no difference really between vectors in 2 dimensions and 3 dimensions, except for you simply have one more extra parameter floating around, okay? So I don't want you to think they're completely separate concepts. Yes? Okay. When we have vectors, the textbook is going to split it into the 2-dimensional ones and then 3-dimensional ones. I don't want you to think that they're actually separate concepts. So what I've done is I've merged those into just one lecture. So what you're seeing is how vectors work as a whole. And then you could actually do a vector in 5 dimensions if you really wanted to. The ideas are all exactly the same. It's just a matter of extension and pattern. And so that's what Calc 3 is going to push you to do. You've all taken calculus. So it's not like you're coming through here with, your arithmetic and times tables. You've done integrals, you've done derivatives. So you've done compartment. And what we're going to do is we're going to extend all of the hardware you've done intuitively into more parameters. So if I have a vector, and I'll introduce you to some notation, because I'm dyslexic, so I don't like words. Now, that symbol right there, raise your hand if you actually know what that is. Some of you had linear algebra with me in the past, so you might have seen this. And this means in. Think of this as the word in. It's the easy way to do it. And I'm going to then write this. It's a double font, it's a double struct R, and then like a superscripted 2. R2, raise your hand if you know what that is, or maybe seen it in a calculus class. Sweet, yeah, the reals, but in 2 dimensions, so the Cartesian plane. So R2 is something with 2 parameters, 2 dimensions that are real numbers. And so if that is the case, then I can describe this vector with these hard bracket notation, and it's going to have how many parameters? So I have 1 parameter there and 1 parameter there, hard bracket. This is the component. I'll write that out so you can see it. This is the component form of vectors. Thumbs up when you've got that. Okay. Notice the difference. Does this have an arrow over the top?
Yes.
Do these have arrows over the top? So is this important? Is notation going to be important?
Yes.
So you have been warned on day 1. Okay, now the nice thing about mathematics is that it's going to push you to extend in something we call mathematical maturity. Nobody can ever finish learning mathematics, it's too big. A baby knows as much math as a postdoc in God's eyes. But there are conventions in how we learn math quicker. And so here, if I were to tell you instead, we have another vector, and I'll call it V. Can you guys see down here, or should I erase and move up? Okay, cool.
The front row is blocking it.
Gotcha.
No, they're too tall.
Don't worry, I'm a 5'5" Korean guy, I understand that. Okay. Yes. So I want to keep this though for comparison. Okay. So now if I have a vector V, and I tell you that this is instead of R2, I say this is an R3. What does common sense say?
3 dimensions.
Dimensions, okay? So then if I'm going to represent this vector V, how many components am I going to have?
3.
You can tell your mom and dad when they call you. I learned arithmetic. And pay tuition for this. Okay. So we have 3 components. If I would have put a 5 there, how many components? If I would have put 7 there, how many components?
7.
Well, gee, if I put n there, how many components?
And
Okay, I'm going to teach you a little notation trick. Because textbooks will just assume that you can figure it out by looking at it, and I won't bully you like that. So I'll show you explicitly what they're talking about. They will try to generalize an idea to n. So like in the same way, is it really new concepts that we're talking about here? No, it's the same thing. We're just increasing this number. It looks different. You'll handwrite something slightly different. What is that concept? Different? No. So that's going to be the key in Calc 3. You're not learning really new concepts. Some of them, but not all of them. And really, a lot of it is that you're going to think is new. It's kind of similar to this. You're simply extending something that you've already known in an intuitive way. So here's how you would do it in general form. So say you have some vector x and you told that this is an Rn. Okay, well, obviously n is not specified. So then all the engineers melt down. They're like, oh no, it's not a number. I can't put it into Chegg. And so the idea is what we can do is discuss this as an index. So the first component we know has to be x1. right?
Mhm.
And we know what the second component has to be too, it's gonna be x2. Once we've established that we are making an ordered list of components, we leave the implication logically with an ellipsis. That fills in whatever number n is going to be. And the very last thing you put, what do you think is going to be the subscript there? Beautiful. That is perfect. Because that's how you would that's how you represent a vector when they don't really specify the exact number. Because again, what's important here is the concept. You're adding components. Is it a different concept? Is it slightly different notation? Sure. But is it different? No. Good. Any questions about any of that?
So in component form, you have vector u is equal to u sub 1, u sub 2.
Mhm.
And above it, you have vector u is in all real numbers for 2 dimensions. So if you have component form vector u, it seems like the assumption is that it's in all real numbers for the 2-dimensional plane. So is there a way to notate vector u for being multiple dimensions than the second dimension without doing in all real numbers of n?
Very good question. So the question is one of context. When are you allowed to assume how many pieces you need, right? Because that's kind of important. The question's context will give that to you. So you'll be, if you're told that you're operating in like just the plane, this is the assumption because you're just in 2 dimensions. But later on, you're going to start dealing with spheres and these paraboloids and these Pringle chip functions. And that's obviously in 3 dimensions. And so then you'll have the context of 3 components. Only later in like past when like fall break do we actually really break into that. I just want you to be familiar with the fact that all that is it's stacking the same idea over and over again. That's a good question. Anything else?
I'm not sure if you covered this in this question, but once we go to 3 dimensions, is it possible to have vectors that only have 2 dimensions, but it's 2 specific dimensions of those 3 dimensions?
Oh, very good question. So what happens if I make one of these 0? One of the components is 0. So that's why this suddenly becomes important. Because now you can have like say in 3 dimensions. That's a good question too. I have a very good question. So here is 3-dimensional space because I am an art major. Now, if I have a vector that is just laying down here, so this is a vector laying down in the plane, it's not going up into the 3rd dimension. However, the context of the environment is 3 dimensions. So if I were to say that, well, V is, even though it's being only housed in 1 plane, it still technically is in a 3-dimensional environment. So I would make that last component, the vertical component, just 0. Because you're allowed to scale that. So there's a lot of freedom in representing these things. Very good. Anything else? Cool. Okay, some practical stuff for computation, and I'll clear this off the board. There are 2 things that get progressively worse with time. It is my eraser quality and my hair. So, well, let's hope that this, I might go by anyone.
Hair or wig?
Well, you'll see the Asian Pro pretty soon. Okay. So, we got to know how to compute these things. That's all cute. You know what an arrow is. That's great. So now we want to be able to do numbers with these things. So here is a standard way to designate a point in the plane. You'll put the capital letter to designate the point and then designate its coordinates right after. So x1 and y1, okay? That's a point, and also I'm gonna make q a point, so we have 2 points involved. So x2, 1, 2. So these are points. Parenthetic over, it's a little bit obvious in context. Now, we know that PQ can form a vector, right? That's the very, very first thing we talked about. So how would you actually realistically compute that? Because these could be any old numbers. And so what this vector is, again, look at this notation. That's the thing. If you are not handwriting and emulating this, it's not going to be a pretty time when you go to do your homework. So I've designed these lecture notes very specifically to make sure it's emphasizing all of the things you would need to be getting familiar with. Okay, so any ideas on what the X component is going to be here?
X1, X2.
Right, it's gonna relate to these two. So if the destination is Q though,
It's
X2 minus X1. And then, again, you don't really have to do much thinking because the components are all going to be parallel. There's so much parallel structure in Calc 3 that once you memorize how one component goes, you've basically got it. Okay, so cool. Let's do numbers. So if I have the point 1, 3 and point 7, 9. And if I want, I'll call this A, I'll call it B. So I want to know what the vector AB is. And then did someone say what? Was that difficult?
very.
Sort of read that,
Okay,
right?
let's do another one. Let's do point C is 17, 0. And point D is -4, -4. Okay, so what is CD?
21.
Right, negative, you gotta get that minus sign there because it's -4, -17. Right, -4, minus. Yeah. Okay. So that's how you use a formula. That's how you study math. You get this out of the book and say, okay, that's the rules. So if I'm going to be given an application of a problem, maybe I just follow the rules. You don't have to reinvent the wheel every time you go to the homework, okay? Is that pretty clear? Because there's something else important about this. We want to know the length of these vectors. So let me erase this. Do you guys know what the distance formula is?
Yeah.
That is my polite way of asking if you passed high school level mathematics before coming to college.
But I don't remember.
Okay, well, this is why we're here to review. So the magnitude EQ is going to be, now there's different ways you could handwrite this. One of them might help certain learners more than others. So I'll put both, okay? It's going to be the square root, it's the house. And you're gonna take x2 minus x1 squared, and then y2 minus y1 squared. So that is going to be your, again, here's the context. And that's going to be the magnitude of this vector. So you see all the components. Here's your first character, the points. Here's your second character, the vector. Now we know how fat the vector is. So sometimes if this is a lot to write, you can actually, I really memorize it like this. I think of it as a change in my x overall, plus an overall change in my y squared. And there's a reason why I do that. Because mentally, whenever I see this, okay, well, that's how you perform that operation. But conceptually, this is going to be more universal. Because notice that these points exist in how many dimensions?
2.
Okay, so fantastic. If you write this formula, it's kind of only working for 2 dimensions. So we need a formula that's going to be easy to remember for any number of dimensions. So here's how we do that. What if we have a point, capital X? And then now let's put these points in 3-dimensional space. So we're gonna have 3 components, right? So x1, y1, and we use z for that third. And then we can have a point capital Y. This can be x2, y2, z2. So, again, is this really going to be a different concept? No, it's going to just simply be an extension. So, if we're going to look at the vector x, y, what might you assimilate from what you already understand into then extending it further?
We're gonna add z.
Okay, let's do it this way. For the class,
Z.
what is the first component?
X2 minus x1.
And then what is the second component?
Y2 minus y1.
Third component.
Z2 minus z1.
So guess what? You basically just derived that. You see how this isn't really about memory as much as it is, I know the characters, I know the plot, I know what's happening. Okay? So here's the real thing, because this is a box in your textbook. And you might try to read it separate and think it's a whole different concept, but really, if you understand how the distance formula works just a plane, is it really a different concept? Is distance suddenly change in 3 dimensions? No, right? So what is the magnitude of x, y?
Square root
Right,
of
you know that there's gonna be a square root, so that we can do that.
change of x squared.
Plus changing x squared plus changing x.
You're already bored because you're too good at this, right? You're just extending what you already know. Okay. If this was 7 dimensions, would it suck to write? Yes. But you could do it. That's the key. So I'm trying to convince you that you have God-given brains, okay? That you can learn how to see a concept instead of just seeing formula boxes. Okay. Now, granted, I have the advantage of probably spending 800 hours on this topic, so I kind of know that. But you can do it, right? So when you're studying on your own, when you're reading through that book, when you're seeing these different things, try not to get lost in the weeds of the symbols. Okay, try not to get lost in the fact that a section is 10 pages long. You have to read 10 pages of the book. Okay, really try to find the story, skim for the important characters, see what they're trying to communicate, and then make sure you can actually extend it. Thumbs up. Okay, any questions about any of this?
Is the magnitude representing absolute value or is it just a symbol?
Very good question. So yes, these are technically like if this was a scalar in there, it's absolute value, but we designate, the 2 bars to indicate this is just the length of a vector. If you want to go on to Calc 5, which is what I'm currently researching, is you double strike those bars because you can have different manifold spaces, and so now you have a norm. But that's different. So basically just know that if you single bars, that's the length of a vector. And if you have a scalar instead of a vector in there, that's absolute value. Cool. Do you guys need to compute something, or is that pretty straightforward how to plug and chug? Okay. And guess what you have? You have homework. So it's not like you're going to escape not having to compute stuff later. So.
Yes.
Oh, since technically today is Friday, I will specify something about those labs. It's not what you think a lab typically is. First of all, because I personally avoid science as much as possible. So lab really is just a set of very specially curated problems that are oriented to the topic matter for the week and what you're going to be studying in that unit. They're designed to push you. They're designed to be hard. I don't expect you to solve all of them, but I do expect you to try all of them. Make sense? That's what most of mathematics is. It's solving problems that you haven't been told how to solve. Because what's the point in being able to follow a recipe? Because anybody and their aunt can make banana bread if they have the directions, okay? So that's what makes you special. You're STEM students. You know how to solve problems. And it's okay to cry about it too if it's hard. But ultimately, you know how to push through and get to the solution on your own. That's what makes you different. Good? Okay. So there's different things you can do with components. If I have, so I'll specify that U and V are going to be in R2. Okay. What does this immediately communicate to you in just one word and some symbols?
2 vectors in the 3rd dimension.
So how many components are they going to have?
3 each.
Fantastic. Okay. So U, and I'll leave it since it's new. I'll put it on. So U1, U2, U3, and then V is going to look like V1, V2, V3. So we can do arithmetic with these, and it'll just basically be like tedious arithmetic. So U plus V, what if you really had a guess how that's going to work? What do you think? Right, component by component by component. So for the first component, what's that going to look like? Perfect. So we take the first component, add those together. Okay, second component, what do you think that's going to be?
U plus 2.
And then the third.
U3 plus V.
Yeah, by the time you get to the third, it's like a minus. Okay. Could that have been a minus sign? Yeah. Okay, good. So both addition and subtraction work that way. Now, here is where it's important to designate between your scalars and your vectors. Okay, because I can now take, so here's, in case you're wondering, you might be like, what happens if that's a 1? Right? That's a decent question to ask. What if there's no number there except for one? So you could have something C in R. Well, R is really just the symbol we use for the set of real numbers. So if you ever see this in the textbook or me write that, just C in R or something in R, that means it's a constant, something like 17 or 4 or -3. That's all that is. So if we take a constant now, notice there's no arrow over it, and multiply that by a vector. No arrow, arrow, no arrow, arrow. And honestly, some of you are thinking this guy is crazy, but you'll go and turn around and turn in your lab with no vector marks. So make sure you actually do that, please. Intuitively, what's going to happen to each of those components? They're all scaled up. So you got CU1, CU2, CU3. I don't even need to teach you anything because that is basically the textbook formula. You're coming up with it. See that? You don't need, you got to learn how to use your books. Okay. Now there are some special unit vectors. Unit means 1. Everyone know what the number 1 is? Okay, good. And then if we then have a length of a vector and we specifically want the vector to have a length of 1, we say unit and the vector. Because that's very, very straightforward. So unit and unit means length of what? Vector means you have 2 components, which are
Direction and magnitude.
well, that's pretty neat. Okay, say it like a Southern Baptist on Sunday morning. Unit means what?
1.
And vector has 2 components.
Direction and
There
magnitude.
we go. Okay. So there are 2 main. These are very common. You've seen this in physics. I hat in 2 dimensions is 1, 0. What if that would have been 3 dimensions? What's the only difference? Yeah, just throw in an extra 0. Okay. And then there is J hat. 2 dimensions. What's that going to look like?
0.
Good. Now, these are in 2 dimensions. If I would have done the unit vectors in 3, I could have done K hat, which is just 0, 0, 1 for that 3rd direction. Now, you're not going to get all of your vectors in just I's and J's. Yes.
I said J hat 0.
Oh, this is the step of length 1 along the x-axis, and this is a step of length 1 up the y-axis. So in the plane, yeah, it's just like that little building box.
So I X J is Y.
Mhm. And then K corresponds to Z. Now, we don't always have vectors that we want to be exactly going that way on the x-axis. We don't always have vectors going exactly up or down on the y-axis. So we have a different idea. So while I erase this, I'll ask you guys a few questions. Shout out the answer. What's 5 divided by 5?
1.
What is 7 divided by 7?
1.
What is square root of 3 over 2 divided by the square root of 3 over 2?
1.
Okay. What is x divided by x?
1.
You're pretty good at that. So you'll be experts at unit vectors, because what you're going to do is you're going to take a vector and divide it just by itself, its own size. Straightforward enough? Because that is going to have length of what?
1.
Exactly. So the magnitude of this vector right here is going to be 1, because you're taking the vector and you're dividing it by its own size. So that's essentially now the extension of saying 5 divided by 5 is 1. Now we say, okay, we have a direction involved, so we haven't got rid of the direction part of this, but the size of this, we've taken the magnitude and just shrunk it down to 1. This will always get you there. So if you memorize this, it's probably on an exam because it's important. Ooh, now everybody starts handwriting. That's really funny. Yeah.
So why do you put the absolute value on the bottom?
Very good question. Technically, vector division is an undefined operation. So really what I want you to think of this as is this is a constant multiple of so this is a scalar number. The magnitude is just going to be a number. So you could really think about it as like this: 1 over whatever the magnitude is, and then multiply that and then shrink down the size of your original vector. So these two mean exactly the same thing: a scalar and a vector. Okay.
So then that would just define the direction and A unit?
The magnitude is going to be 1 because we're specifically dividing this vector by how long it is. So in the same way that if you take 7 and divide it by exactly 7, you'll go back to 1. So if I take this direction and it's a certain size, remember that when I drew the super long vector and this really short, well, this is just a number. So it's basically scaling down the size or shrinking it back down so that it'll always come back to 1. Is that good? So that's what the formula is doing. In reality, when you're doing a computation, you'll just slam it to the, And since now you know how to find the magnitudes with computation, you're all set. It's a building blocks. Now, there is a way, if you have components, here's a formula that you'll find very useful. So, I'll just say the hot word so everyone writes this down. Exam, okay? If you have a vector u, and let's make it 2-dimensional, and then I'll extend it. Well, actually, you guys will extend it. You're smart enough. So then that means there are how many components here? Okay, so it's u1, u2. Now, if you're given the component form, you don't have to go through the rigmarole of like taking the distance, because this is defined, the position vector is assumed that this originated from the origin. Okay, so the way you can do that then is the magnitude of just a given component vector like that is going to be just the square root of the components squared, like that. Much easier. And this is thankfully how most of them are going to be. This is going to be magnitude component form. And I believe if I increase that to a number 3, you'd all know exactly what this is going to look like, right? Because all you're doing is tacking on, oh, I have another component. Questions about magnitude from component form or from the formula for a unit vector? Right? I want everybody to get ready to make a finger gun with their hand, right hand. Right hand's up. Now make a finger gun like this. And then point it at the person you dislike in it. No, I'm kidding. All right. So what you're gonna do is you're going to take your middle finger and then move it like in a box at 30 degrees, right? Okay. Now I promise this is not a tattoo, but take your pen and put X on your pointer finger, okay? And your thumb, put Z. Put Z on your thumb. And then Y is your middle finger that you like put out after making your finger. This is the orientation of how 3-dimensional coordinate space works. That's the relationship between X, Y, and Z, always. Okay, so there you go. Now you know the right-hand rule. I know physics has their own right-hand rules, but physics is kind of ridiculous. So, oh, okay. So in 4 minutes, we're going to extend some things that you should be familiar with. Because there's like a right-hand rule for ampere law, and then another one for Kirchhoff.
It was a weird orientation.
Okay, guys, dialed in. You only got a few more minutes. We're practicing extending ideas. So, oh, this is about to be fun. Let's see how many of you guys remember this from SAT math. Let's see. X minus h squared plus y minus k squared equals r squared.
Circle.
That's a circle. Okay, so what's the 3-dimensional version of a circle?
Sphere.
Is that form really going to change that much?
No.
What have we been doing this entire lecture? Just their dimension and just add it on. So when you have equations of spheres, I'm not going to show it to you because guess what? I'm going to upload the textbook readings and you get to sit down with your cup of coffee and read some math. And you're going to see that the equations are exactly like a circle.
What if we don't drink coffee?
Well, you can drink your tears if you cry a lot. So here, because this is an equal sign though, this is something that is when I'm talking about details start to matter. Is that this is a circle, sure, but points on this has to be equal to. So this equation is a very specific set of points. It's only the boundary of the circle. Okay, so if I put that right there, is that a solution to this equation? But it's inside the circle, why not?
Solutions that only.
Right, because this equal sign is restricting. So if I wanted to not just have a circle, but I wanted to have a paper mat plate, all right? Then I'm going to change this to what?
It's usually not less than.
What do you think it's gonna be? It can't be equal, so you only got two options.
Less than or equal to.
It's gonna be inside, and if it's gonna be inside, less than, yes. So if I take x minus h squared plus y minus k squared less than and equal to r squared, because I still want to include the boundary. Now is that point part of that plate? Why?
Because that's less than small.
Fantastic. So it should come as zero surprise to you when the sphere has an equal sign and the solid ball uses less than or equal to. Right? Because it's the same exact concept. We're just representing it differently. Good.
Yeah.
Okay. And that's why mathematicians go crazy, because we start saying, hey, technically, if I just keep adding stuff on, I can have a 10-dimensional ball. That's hilarious. So they'll do stuff like that. Can you visualize that? No. Does it exist? It does.
Draw it.
So, are there any questions about any of what we've talked about today? Okay, here's my expectation for you. Try, because if you don't, you'll fail. That's how Calc 3 works. I think a lot of people think that they can get through this like they get through their straight line statistics. I will say this, okay? I am not yet a professor. I study with people your age, and I study with people in your major, and I've been doing this for the last 3 graduating classes of engineers. I know how you guys study, okay? So you cannot fool me. Here's how this works. You're gonna do the readings. I'm gonna upload those tonight to the D2L. It's gonna be the sections that are on the calendar. And you're going to read them, right?
Yeah.
Okay, at least you agree that you say you're gonna read them. And then what's gonna happen is every single lecture, I'm going to ask one question at the start of class that you would only know the answer to if you actually read the readings. Okay? And the people who know the answer to that question are going to get an A in the class. By nature, because you have done the work. Okay, math is very unforgiving to lazy people, and I don't want you to be in that category of people. Got it?
Mhm.
So I will do everything in my humanly power, God help me, to make sure every single one of your questions gets answered. Every single concern you have about the class is addressed, and that every single concept is explained to you until it is sufficiently clear. Yes.
Will practice set problems be assigned or will they be our own duties?
They will be on the Pearson once we figure out tech, because tech is being ridiculous right now. But yeah, don't worry about that. But yes, I'll put my email to make sure it's clear on D2L. Please reach out.
Is Pearson being obnoxious for all courses?
Correct. Locke was having issues with it this morning too. Tell
Okay.
you.
So it's
Because static was like, you can get in, no, we can.
I'm pretty sure only Cengage hasn't died yet. So we'll be.
Bye. Thank you. This all, Scott, ordered today. We appreciate your lecture. Very good. I want to talk about scheduling because I know that some of you do have to go immediately after this to get to the NEC. That's not a trivial thing to do. I have a proposal, but I can only say it if everyone agrees, which we could start 10 minutes earlier. We could start at 1, so it wasn't hard to forget. I find if there are weird numbers, people kind of, we could say we're gonna start at 1 and be done like at 2 or 1:55. Are you available for that?
Mhm.
Okay. How would you feel about if we just had our class starting at 1?
Yeah.
Would that work for everybody?
Mhm.
And then you could more leisurely go to your next class. Okay, we'll do that. So please don't forget, put it on your calendar. I'll put it on mine now, but this class will start at 1. Okay?
All right, I'll see you guys on Monday.
Yeah.
Jim,